We will discuss now about cells, definition of EMF and internal resistance of the cell. Internal resistance of the cell. So this is the present topic. Later we will discuss about series and parallel combination of cells. So a cell is a device or a mechanism which supplies a constant potential or constant energy to the charge carriers to pass through a conductor. So it applies a constant electric field so that a steady current flows through the conductor. Such an external arrangement is called as a cell. And the energy provided by the cell per unit charge to pass through the circuit, we call it as EMF of the cell. So let us derive a simple formula for EMF and internal resistance. What is the relation between those two? Consider a chemical cell. A chemical cell consists of an electrolyte solution. An electrolyte, let us suppose it's an electrolyte, and it has two electrodes. So let us say this is the positive electrode and here is a negative electrode, say N. Now suppose these two electrodes are connected by means of an external resistance like this. So let us argue the resistance. Now you can make the circuit or break the circuit by using a key. Okay. So here let us suppose the potential of the positive terminal or this positive electrode with respect to the electrolyte is V plus. Similarly, the potential of N, that is a negative electrode, with respect to the electrolyte V, say V minus. Now, when no current is flowing through the circuit, the electrolyte will have the same potential difference or it will have the same potential throughout its length or throughout the electrolytic solution or electrolyte. The potential difference is constant when no current is flowing. Now, when current flows in the external circuit, if you insert the key or if you put the switch in on position, let us suppose a current I flows through the circuit. Now, the current flows in the external circuit from P to N like this, whereas inside the electrolyte it passes from N to P. Okay. Now that means it will continuously supply negative charges to P. Of course, the positive ions will drift towards the negative electrode in the opposite direction of the current. So in the closed circuit, we call this as closed circuit, the current is flowing through the resistor in this direction externally, whereas inside the cell it flows from negative terminal to positive terminal. So to show that it is a positive terminal, it is a negative terminal, in any electrical circuit, a cell is represented symbolically like this. This line is bigger than this. So this indicates positive potential, this indicates negative potential. Now, the potential difference between let us say this is a point A, this is point B. So that is V. The potential difference across this is nothing but let us call it as V. So from our formula, if I is the current, say some I is the current, R resistance, V is equal to IR externally. Now when we come to this inside of the cell, so we can write like this. The total potential difference between P and N is between P and the electrolyte V plus and between this negative terminal and the electrolyte, that is V minus. Suppose in the absence of any current, then this potential difference we call it as EMF of the cell. So in the absence of any current, so this quantity is called as EMF of the cell, V plus and V minus. So total potential difference between P and electrolyte and N and the electrolyte. So that is called as the EMF of the cell. Then since a current is passing here, the electrolyte will offer some resistance to the flow of charge carriers, because the electrons when passing through the electrolyte will be getting neutralized by some of the electrons will be neutralized by the positive ions coming from P to N side. So the current or the electrons colliding with the ions or interacting with the ions or positive ions will lose their energy, or they may get neutralized. Therefore, to overcome that resistance offered by the ions in the electrolyte, some energy will be used by the charge carriers to overcome that resistance. So the resistance of an electrolyte is due to the ions that are present inside the electrolyte. Therefore, if the distance between the electrolytes increases, the electrical distance inside the cell also increases. If the area of cross section of the electrolytes increases, or the area of cross section, if you consider it as the area of cross section of the electrolyte, then the resistance decreases. So the distance offered by the electrolyte to the flow of electrons from N to P is called the internal distance. So if that is represented by a letter R, so let us call this as internal resistance. Internal resistance of the cell. Then this equation will become minus IR, where I is the current in the circuit. So V plus V minus IR. So why not take a minus sign means the current is moving in the opposite direction to the external current direction. When compared with this, here it is going from N to P. That's why you have taken the negative sign. Therefore, we write like this: E is equal to, this is EMF of the cell minus IR. Minus IR. Or from this, we can say R is equal to EMF of the cell minus potential difference by the current through the circuit. So, internal resistance of a cell can be calculated from this formula. If V is the potential difference between the across the resistor, external resistor, and EMF of the cell is actually E, then internal resistance of the cell is given by that formula. Okay, so actually this EMF is a misnomer. This EMF, this word is a misnomer because actual potential EMF is nothing but potential difference between the terminals of the battery or the cell when the circuit is open. Open means no current is flowing externally or between the electrodes. That we call it as open circuit. So EMF is defined as potential difference between the electrodes when the cell is open. And this is actually the energy supplied per unit charge by the cell for continuous flow of the charge inside the closed circuit. Per unit charge, how much energy is supplied by the cell or battery. So that is actually EMF. So EMF is actually work done by the cell or energy supplied by the cell per unit charge. So it is not a force, but that word is used well before the process of electrical conduction in the cell is known. So in those days, scientists doesn't know how this electrical conduction takes place in the cell. That's why they call it as some sort of force driving the charges inside the cell and gave that name EMF. So conventionally, We are using the same word for EMF. So actually that is a misnomer. Now, so the interactions of a cell depends upon the distance between the electrolytes, cross section of the electrolytic substance or the medium, and also on the nature of the electrolyte. So these are the factors on which interactions of a cell depends. Generally, the resistance of a cell will be very small. We may neglect for practical applications, but in some cases it will be comparable with the external distance. So for an ideal cell, the interresistance is considered to be 0. Now we will go to series and the parallel combination of cells. Let us see what is the effective EMF in case of parallel and series connection of the cells. So now we will talk about series combination, series connection of cells. Now in series connection, if the cells are connected like this, so in series connection the cells are connected one after the other such that the negative terminal of one cell is connected to the positive terminal of another cell, and so on. So there is only one path for the current to pass through the cells. So this connection is called a series connection. So let us consider this is a cell of EMF E1 with interresistance R1, and this is a cell of EMF E2 with interresistance R2. And consider a point here as A. Here I say some B, here I say some C. Now I want to know the potential difference across A and C. So let us call it as V. So it is just nothing but potential difference across VA minus VB plus potential difference across VB minus VC. So as you have seen, since current is flowing through a cell having interresistance, this can be written as E1 minus IR1. So let us suppose I be the current through the series combination. So this plus E2 minus IR2. Now therefore I can write like this: E1 plus E2 minus I into R1 plus R2. Therefore, comparing this with the standard equation, so V is equal to the equivalent EMF minus equivalent internal resistance. So, and here the parameter. So, comparing with this equation, from this we can say that the equivalent EMF is E1 plus E2. And equivalent interresistance of such a cell is R1 plus R2. So it means you can replace this series combination by a single cell. A single cell having equivalent EMF and equivalent interresistance. So that can be replaced by a single cell whose EMF is given by this formula and interresistance is given by this formula. Now you can connect any number of cells like this. So then in such case for n number of cells, in series, so we can write the equivalent E1 plus E2 plus and so on plus En, and similarly R equivalent is given by R1 plus R2 plus and so on plus Rn. So like this. Suppose if one of the cells is reversed, then what you have to do? So but the method is, if the cell is giving out the current, we call it as discharging. So it is something like that. So as you have seen earlier case, if the current is coming out, let us suppose like this, with EMF E and R. So V is equal to E minus IR. So in this case, so if we say it is discharging. Suppose if the current is going in like this, here V is equal to E plus IR. So this is the charging. So charging of the battery of a cell. So you know very well about this. So this is charging the cell. This is the discharging the cell. So here the current is going from plus to minus. It is coming out from positive terminal and then entering into the negative terminal. Whereas inside the cell, here it is N to P, that is negative terminal to positive terminal. Here it is positive to negative. In such case, the direction of the current inside the cell is getting reversed. Hence, in such case, we put minus of here minus I. Therefore, that will be plus. So, when compared to these two, here it is discharging, here it is charging. Here, the potential difference across the terminals of the cell decreases. Here, it will be more than its EMF increases. So, that's why you should remember there is a difference between these two. So, if one of the cells is reversed, then suppose E2 is reversed. If E2 is reversed, then it is to be taken as minus E2. So, if the cell is reversed, take the direction of EMF as minus. But the resistance value doesn't change. The resistance has no direction. So, whether the current flows from left to right or right to left, the resistance value doesn't change. The formula for the equivalent resistance or effective resistance doesn't change. But only the sign of the EMF used in the equivalent EMF equation must be reversed. Okay. Now we will go for this is series. We will go for parallel combination. Series is over. Now parallel. Second one. Parallel connection of cells. Suppose two cells are connected like this. So this is a cell with EMF E1 and interresistance R1, and this is a cell E2 EMF R2 like this. So, some positive from this it is coming. So, let us suppose the first cell gives a current of say I1. This is giving a current of say I2. These two combined become I. So, let us complete this. So, it is assumed to be a closed cell. So, I is equal to I1 plus I2. So, if the positive terminals are one side terminals are connected to one point, other side terminals of the cells are connected to another point, then it is called a parallel combination or parallel connection. In this case, the current through different cells will be different. It is not as in case of series. So, irrespective of the EMF in series, same current passes. Here, different current passes through the cells in parallel connection, or the main current has actually branches out at the junctions, but the joining point, what is happening? The current is branching out, or here it combines and then becomes I. So, if the current is going like that, then it branches out. Therefore, through different branches, currents are different. Whereas in series, we don't have such different branches. Okay. So, total current in this connection is given by I is equal to I1 plus I2. Suppose we take how do you calculate this I1 and I2? So I1 is we know the potential difference across V1 and V2. If suppose it is V between these 2 points, then that is EMF of the cell minus through the first cell current is I1. So minus I1 R2. Therefore, I1 can be written as E1 minus V by R1. Suppose V is the potential potential difference across these 2 points B and B1 and B2 are across A and C. So it is one and the same. So let us assume the same. Hence, PD across B1, B2, whether you calculate with respect to B1 or with respect to B2 must be same B. So that's why I have taken B as equal to potential difference between B1, B2 or A and C is given by E1 minus I1 R1. Hence, I1 is equal to E1 minus V by R1. Similarly, potential difference can also, the potential difference, for the reference I will write like this, B1, B2. V can be written as, in terms of the IMF of the second cell, so that is E2 minus I2 R2. Sorry, so therefore, I2 is given by E2 minus V by R2. Therefore, total current. So, therefore, I is equal to, so sum up these two. So that is E1 minus V by R1 plus E2 minus V by R2. Okay, here you can take this E1 by R1 plus E2 by R2 minus V into 1 by R1 plus 1 by R2. So from this equation, the total current in the circuit is given by this. So you can compare with so that is I is equal to the EMF equivalent by effective or equivalent internal resistance minus potential difference by into R1 by R equivalent. Like this you can write. So R we can say, yeah, this is nothing but 1 by R equivalent. Hence, you can compare this equation with this equation. So comparing them, you can say that, so that is nothing but, so how do you got this formula is I is equal to, because from our formula, general formula is V by R. So that is the Ohm's law. We use the Ohm's law and we have written it for our convenience like this. So comparing this equation with this, we can easily say that the effective or equivalent EMF by equivalent internal resistance is given by E1 by R1 plus E2 by R2, and similarly 1 by reciprocal of equivalent resistance, internal resistance is given by R1 plus R2. So in that way we can find out the effective or equivalent EMF. So this combination can be replaced by a single cell whose equivalent EMF can be found from this formula and whose effective resistance can be found from this formula. Now, if you have several such cells connected parallel, then what is that formula in such case? So that is, if n cells are connected like this, so same formula you can use. Equivalent EMF by equivalent internal resistance is equal to E1 by R1 plus E2 by R2 plus and so on plus En by Rn. So that is how we find out for equivalent EMF. And similarly, equivalent internal resistance is given by 1 by R1 plus 1 by R2 plus and so on 1 by R1. So Rn. So that is the reciprocal of equivalent interactions of such as combination is given by sum of the reciprocals of individual internal resistances of the cells. Now, suppose if one of the cell connection is reversed, then you have to change the sign of E. Suppose E2 is reversed, then you have to put minus E2. Let's see the formula, only the sign of the EMF of the cell which is in reverse connection, you have to change the sign. But resistance doesn't change, only this the sign of the cell which is reversed. Its EMF must be given the negative sign in the expression. In that way, you can find out equivalent EMF of a cell. So that is about parallel connection of cells. Okay. Next we will discuss in the next class. We will discuss about the Kirchhoff's laws and application of Kirchhoff's laws.